we were thinking about the big picture in machine learning, and we saw how by starting from the basic idea of trying to minimize our expected loss, sort of thinking clearly about what we really want to do, we found that the key quantity that we needed to solve this problem were these conditional distributions. The key quantities, I should say. So it's a whole set of quantities, but it's these conditional distributions on y given x. And then we found that when we parameterized the model with some parameters or latent variables, that in order to get that thing, given our data and x, that we needed to solve this sum or integral over the values of theta. And we observed that this is often intractable, or we claimed that at least, and it turns out that it is. And so let me just give you, before we move on, to start to look at all the methods that play into, or how they fit into solving this problem, or parts of it. This is often called the predictive distribution on y. This part is often called the posterior distribution on theta, given posterior distribution on theta on new parameters. It's a little bit of terminology. And now we're ready to look at the different core ideas and methods in machine learning. So the first approach that you might take to solve this would be to say, well, let's avoid the problem altogether. Let's make it tractable by assuming some distribution, some model, for which we can do this exactly. So the first approach would be go for exact inference. Assume a nice enough model that you can do this, at least for parts of it. So here's some methods which facilitate exact inference, if not for the whole thing, at least for parts of this problem. So multivariate Gaussians are very nice distributions. And oftentimes with multivariate Gaussians, you can do everything analytically and it just works out beautifully. So multivariate Gaussians are very nice. Also, a tool which is used to facilitate parts of this, doing parts of this computation exactly, are conjugate priors. And in some cases, graphical models, for some types of simple graphical models, you can use dynamic programming to do exact inference for parts of this problem at least. So that's one class of methods is enabling exact inference for parts or all of this problem. It's usually not possible. So in more general and more interesting models, you have to resort to something else. And the simplest other way that you might solve this problem is to use point estimates of theta. And the typical point estimates that you would use would be, for example, the maximum likelihood estimate of theta or the maximum a posteriori estimate of theta. And let me tell you how these are used. So let me define briefly. The maximum a posteriori estimate of theta is the value of theta that maximizes the posterior distribution. This is the posterior. That's the map. We call it the map. And then you would approximate this predictive distribution on y by, it's an approximation, crude approximation, by taking essentially a point mass at theta map. You would approximate the posterior by a point mass at theta map, and this would become just this part where you plug in theta map. So writing this as an integral, d theta, is not really very rigorous to justify that, but you can, if it was a sum, you could do that, or you could make it a measure, more generally, and justify this in this way. And you can use a similar justification for the MLE. So some other, well, so in order to solve for these, sometimes you can do it directly, but sometimes you need to use optimization techniques. So optimization techniques are important in machine learning, and expectation maximization, or EM, is one very particular type of way to optimize and to solve for these types of values. At least approximately. So now, the third type of approach. Oh, and let me also mention for that one, empirical Bayes is, it sort of fits into this section. You are optimizing, so you're taking a point estimate for part of theta, but not all of theta. So that's sort of empirical Bayes. We'll talk about that more later. C, the third option, and so these are not necessarily disjoint. Many methods will combine many of these different techniques. The third class of techniques is deterministic approximations. And these would include things like, so by deterministic approximation I mean you're using some method to deterministically approximate this integral. And examples of this would be the Laplace approximation. Another example is variational methods. And yet another is called expectation propagation. And the fourth category of methods to solve this intractable problem, or at least parts of it, is stochastic approximations. Very popular, and typically very simple to implement. And these would include Markov chain Monte Carlo, MCMC, such as Gibbs sampling or Metropolis Hastings, two types of MCMC techniques, or importance sampling. Importance sampling is a way to approximate expected values. So importance sampling, and a particularly important type of importance sampling is particle filtering. It's sort of a sequential importance sampling. So these are sort of the core, all these things that I've listed out here are sort of the core concepts and methods in machine learning. And they all arise in a very natural way, as we've seen, from trying to solve this fundamental problem, which often is intractable. So this is the big picture. This is how all these pieces fit together. You can think of them all as coming back to trying to solve this problem, which arose from trying to solve our original motivation, which was minimizing our expected loss from a decision theoretic perspective, and trying to find these conditional distributions on the y.